All right, let's jump right in. Today, we're looking at an idea that is so elegant, so wild, it might just change how you see the universe. What if the most fundamental things in existence aren't tiny little dots, but are actually knots? Knots tied in the very fabric of reality.
You know, it all starts with one of the most stubborn mysteries in all of physics. We've got these fundamental particles, right? And they come in three generations. Basically, you have the electron and then two heavier, unstable copies of it. But why do they have those exact masses? And maybe even weirder, why does it just stop at 3?
And this isn't just some trivial question. The Standard Model, for all its amazing success, has absolutely no answer. It's like having a cookbook that lists ingredients but gives you no idea why they work together. It's a huge gap in our understanding, and it's had physicists scratching their heads for decades. Okay, so the material we're digging into today comes at this with a totally radical idea. It starts with this one core belief, this axiom. What if particles aren't points at all? What if they are stable, tangled knots in the fabric of space itself? Basically, imperfections that we perceive as matter.
And what's wild is that this isn't a totally new concept. It's actually a really old idea, dusted off and given new life. Way back in the 1800s, Lord Kelvin had this vision of atoms as little whirlpools knotted up in something called the ether. Now, the ether theory didn't pan out, but that central thought, that the shape of things could define reality, well, it seems it was just waiting for the right time.
So let's call this the knot hypothesis. The claim is simple. A particle's mass is just the energy it takes to twist spacetime into that specific knot. The more complex the knot, the more energy, and therefore the more mass. It sounds beautiful, but the real question is, does it actually work? Let's put it to the test. Okay, so the theory starts with the simplest possible stable knot you can make, a trefoil knot, the one with 3 crossings. This, the model proposes, is the electron. It's the ground floor, it's the most basic, stable particle, and its mass is our starting point for everything else. Now, take a look at this. This visual is everything. On the left, there's our electron, the simple 3-crossing trefoil knot. In the middle, you've got the muon. It's a more complicated knot with 5 crossings. And then way over on the right, the tau, with 6 crossings. The idea is so clear here. As the knot gets more tangled, the mass goes up. So let's climb what the theory calls the lepton ladder and see if the numbers actually line up. This is where the rubber meets the road, you know? This is where a cool idea either becomes a real scientific theory or it just stays a nice little thought experiment. Can it predict the other masses, starting only with the electron? So let's look at the muon, our 5-crossing knot. The theory gives us a surprisingly simple formula. You just take the electron's mass and you multiply by a factor that represents the stiffness of spacetime. That's it. It directly connects the knot's geometry to its mass. So what happens when you plug in the numbers? Well, the theory predicts the muon's mass should be 105.96 million electron volts. And the actual measured value from experiments? It's 105.66. I mean, just look at those numbers. They are practically on top of each other.
How close is that? The difference is a tiny 0.28%. That's not just a good guess, that's an absolutely incredible prediction from such a simple foundational idea. This is the kind of thing that makes you really pay attention.
Okay, but what about the next step up? The super heavy tau particle, the 6-crossing knot. Well, now the knot is getting so tight, so cramped, that it takes extra energy just to bend space that much. Think of it like trying to tie a knot in a really thick, stiff rope. The theory actually accounts for this, calling it a curvature penalty, and adding a new little term to the equation. And when you run the calculation with that new penalty factor, you get a prediction of 1768.4 MeV. The real observed mass, 1776.86 MeV, and wow. It works again. The theory just nailed it. This time, the error is less than 0.5%. And what's so amazing here is that the model didn't just guess the next number. It correctly predicted that the rules had to change a little for more complex knots, and it predicted how they would change with pinpoint accuracy. So, the model has perfectly explained the 3 particles we know about. But this brings us right back to the original mystery, and now it's even more urgent. Why does it stop at 3? A good theory has to explain this too. It has to explain why the ladder just ends. And it does. It describes a failure mechanism.
It says a hypothetical 7-crossing knot would need to be tied so tightly, the stress would literally be too much for the fabric of space-time to handle. The vacuum itself would basically break or liquefy at that point. The knot just couldn't form. It would fall apart before it could ever become a stable particle. There's a physical limit.
So, the theory has just given us this incredibly elegant explanation for the whole lepton family. Amazing! But that's only half the periodic table, right? What about the particles made of quarks, like protons and neutrons? Can knots explain them too? You bet it can. The idea is that quarks are like open loops that are designed to be linked together. So for something like a proton or a neutron, you get 3 of these quark loops braided together in this really cool pattern called Borromean rings. It's a special configuration where no 2 rings are linked, but all 3 together are inseparable.
And this is where it gets truly mind-bendingly beautiful. To calculate the mass of this braid, the theory needs a factor to account for its stability. And it turns out that factor is the golden ratio. Yes, that golden ratio, the famous number that shows up in art, architecture, and all over nature in the most stable and beautiful structures.
So, for the grand finale, what do the numbers say? With the golden ratio baked into the math, the model predicts a neutron mass of 940.8 MeV. The measured mass is 939.6 MeV. It's just another perfect bullseye.
Just think about that. We're talking about an error of just over 0.1%. This is the 3rd major type of particle, predicted with this insane accuracy, all from one single, simple idea. Particles are knots. At some point, you have to stop calling it a coincidence.
Okay, let's just pull back for a second and really think about what this theory has done. It started with one simple premise, and from it predicted the mass ratios for an entire family of particles. It explained why that family has to end, and then it went on to calculate the mass of a completely different kind of particle.
And that's really the heart of it. This isn't just some clever math that happens to fit the numbers. The source material really drives this home. It provides a physical reason for things. It tells us why particles have mass. It's the energy stored in their twisted shape. And it explains why there are only 3 generations, because the fabric of reality itself has a breaking point. And that leaves us with this huge, fascinating final question. If this is right, if matter is just knotted space and mass is just stored energy, what else does that mean for our universe? The source even hints that things like dark energy might be the leftover tension in spacetime from knots that failed to form. It really makes you wonder. Maybe reality is just one big, beautiful, tangled puzzle waiting for us to figure out how to untie it.